Hello everyone, this is Ellen from the Experience Research Lab. Today I'll show you how to run a linear regression in Microsoft Excel. If you had a chance to watch the previous video on how to run discriminant analysis in SPSS, you might be wondering why all of a sudden I should change the platform to Microsoft Excel. As a researcher and data analyst, I've been using SPSS for almost a decade now, and having analyzed hundreds of data sets, I wouldn't hesitate to say that SPSS is indeed one of the most robust data analysis tools. SPSS supports a wide range of data analysis from descriptive statistics on data frequencies to orthogonal designs for conjoint analysis. What I love most about SPSS is that it gives me so many options that allow me to configure the setting for the analysis. Last but not least, and actually this is the most important, is that SPSS delivers very well structured and detailed outputs. However, along with the advanced statistical analysis capability, SPSS comes with a price. As you can see here, the lowest price is $99 per month. This is considerably higher than Microsoft Excel, which costs less than $5 monthly. By default, Microsoft Excel may not cover all types of analysis supported by SPSS. It cannot even read SPSS files, not to mention import them directly to the platform. As you can see here, I have so many sample files and datasets, and if I right-click on one of the files and click Properties, I can see that most of these files are SPSS data documents in .sav format. Unfortunately, my SPSS subscription just expired before I had a chance to save and convert these files to CSV format or other formats readable by Excel. So now I only have Microsoft Excel with me, and if I click File, Open, and then browse the locations of the folder that I mentioned earlier on, I wouldn't be able to see any of those SPSS files because Microsoft Excel cannot read them. So that's the problem with Microsoft Excel, and fortunately there's a solution to it. By paying an extra of $1 for the professional package of Colectica, I can import such files not only from SPSS but also from Stata and SAS directly to Microsoft Excel. And to analyze the data, I can have the Microsoft Excel add-ins that allow me to run several analyses, including ANOVA, correlation, covariance, descriptive statistics, down to z-test. And if I want to go further to run more advanced statistical analysis, I can download and install RealStats package that is literally free of charge. With Colectica, I can easily import SPSS files by going to Data and clicking from SPSS. Alternatively, I can hover my mouse to Colectica and click from SPSS. Either way, a window will pop up advising me to locate the folder where the file and dataset I want to analyze belongs. So the file name is car sales. So I just click on the file and click Open. And to import the file directly to Microsoft Excel, I just click Import. So this is how the dataset imported from SPSS looks in Microsoft Excel. On the right pane here, I can see the details of the dataset, which has 11 columns. And if I click on one of the columns, I can see the variable details, which are pretty similar to the details in SPSS. So there is label here, data type, minimum and maximum length, measurement unit, and row. Whenever and wherever necessary, I can add, edit, or delete the details. However, since the objective of my video today is to show you how to run linear regression in Microsoft Excel, let us talk about modifying the details later in the other videos. As mentioned in the previous video, linear regression is related to discriminant analysis because both use independent scale variable to predict the dependent. The difference is that the discriminant analysis is for a categorical dependent variable, while the linear regression is for numerical variable using scale measure. So it is a predicting group versus predicting value. In this dataset, the dependent variable is sales, which is in $1,000, while the independent variables are price, also in $1,000, engine size, horsepower, wheelbase, curb weight, fuel capacity, and fuel efficiency. And to predict the sales using these 7 variables, I need to go to data and then click data analysis. Subsequently, another dialog box will pop up listing all types of analysis supported by Microsoft Excel. I just need to scroll down and find regression here, click on it and click OK. The input y range is for the dependent variable, which is cells in column C. So I just click on this cell and then drag my mouse down to the last row, which is in row number 158. Input x range is for the independent variables, which are column D to column J. So just scroll up. So column D to column J. Since there are 158 rows, I just type 158 here. I want to have the labels printed on the output and be confident that there is only 5% chance of being wrong. So I just click confidence interval as 95%. What I like most about running analysis in Microsoft Excel is that it gives me flexibility to save the output within my active worksheet, in a new worksheet, or even in a new workbook. But for this video, I'll go with this first option to save the output in the first row of column M. So just click here. And then I want to see the residuals and also normal probability plots. Click OK. As you can see here, there is a warning saying that regression function returns error. Please check input ranges again. So just click OK and then click cancel to solve the problem. The problem is that linear regression in Microsoft Excel cannot work with missing values or empty cells. If I click on this column and then go to home and then sort the data from smallest to largest and then click Ctrl N, there's no problem in this column. But if I click the next column and then sort again from smallest to largest, I can see there are 2 rows with empty cells here. So I have 2 options here, either to remove the rows with empty cells or to replace the missing values in every empty cell with the mean or average of every column. For this video, I'll go with the first option, which is to remove the rows with empty cells. So just click delete here. Now I'll go to the next column, column E, and then sort the data again from smallest to largest. There's no problem now. How about column F? No problem either. Column G is good. Column H, there is 1 row with empty cell here, so just remove it again. And then column I, it's good. How about column J? So there are 2 rows with empty cells. I just remove it again. Now I only have 153 rows left, and I will rerun the linear regression by clicking data and then clicking data analysis. Find the regression here and then click OK. So since I only have 153 rows left in my dataset, I just change this to 153 and this one as well to 153. Everything else is the same. I click OK. And this is the summary output. I just close this one to have a better view of the output, and then go to home, click this. The first table is the regression statistics. Multiple R refers to the correlation coefficients, which tells me the strength of the linear relationship between the dependent and independent variables. A multiple R of 0.56 indicates a moderate positive relationship between cells and the given independent variables. R squared shows the proportion of the variance for a dependent variable explained by the independent variables in the model. The higher the value, the better it is. In scientific research, R squared is supposed to be higher than 0.6. However, in marketing and social research, it can be as low as 0.1. That is to say that an R squared of 0.31 here is not necessarily a bad sign. The standard error provides the absolute measure of the typical distance between data points and the regression line. Since the dependent variable is cells in $1,000, the standard error also uses the same unit, which is $1,000. The lower the value, the better it is. The standard error of 58.49 here says that the predicted cells can be $58,490,000 higher or lower than the observations. Is it a good thing? Let's find out. As mentioned earlier on, there are 152 cases analyzed. This is the number of observations. Regression df stands for degree of freedom, which refers to the number of independent variables used in the model. Since there are 7 independent variables, regression df is 7. Meanwhile, the residual df refers to the number of cases minus the number of all variables. So there are 152 cases and 7 independent variables plus 1 dependent variables, total 8 variables. So 152 minus 8 equals 144. SS stands for sum of square regression. It refers to the sum of the differences between the predicted value and the mean of the dependent variable. Meanwhile, MS here stands for the mean of the sum squares, which equals the sum squares here divided by the degrees of freedom. Therefore, regression MS here equals regression SS divided by regression DF, which is 32,131.48. The residual MS equals residual SS divided by residual DF, which is 3,421.58. The F value is the ratio of the explained variance to the unexplained ones. The higher the value, the better the model is. In this case, F equals regression MS divided by residual MS, which is 9.39. The significance F shows the probability for the model to be wrong. Since it is lower than 0.001, I can say that the model fits the data. So coefficients in the table are what I need to formulate the equation for the model. So cells equals minus 226.22 minus 0.4 multiplied by price plus 34.11 multiplied by engine size minus 0.58 multiplied by horsepower plus 4.54 multiplied by wheelbase minus 51.21 multiplied by curb weight plus 0.49 multiplied by fuel capacity minus 1.27 multiplied by fuel efficiency. It turns out that sales have negative linear relationship with price, horsepower, curb weight, and fuel efficiency. Every $1,000 increases in price will result in $400 decrease in sales. On the other hand, sales have positive linear relationship with the engine size, wheelbase, and fuel capacity. A 1 liter increase in engine size means an extra $34,1100 in sales. The standard error in this table tells pretty much the same information as the standard error in the first table here. The difference is that the standard error in the third table here only refers to the data points in the corresponding variable. So looking at the standard error of the horsepower, for example, I can say that the predicted sales can be $240 higher or lower than observations. T-statistics or T-stat equals the coefficients divided by the standard error. So for the wheelbase, T-stat equals 4.54 divided by 0.92, which is 4.91. It doesn't say much about the model except for small sample size. Therefore, I need to check the p-value for each coefficient. A small p-value lower than 0.05 indicates a significant relationship between the dependent and independent variables. Out of these 7 independent variables, only 4 that show significant relationship with the sales. They are engine size, horsepower, wheelbase, and curb weight. Considering this, I'll try to increase the R-square by removing the other 3 variables: price, fuel capacity, and fuel efficiency. To do that, I can rerun the analysis for the 4 independent variables by going to data and then clicking data analysis. Select regression, click OK. The input Y range stays as it is, however, the input X range is now the first row of column E. Just change it to E, and to column H. Everything else remains the same, so I just click OK. So there is a warning saying that output range will override existing data. So I don't have a problem with it. I just click OK. Go to home and then click this one. As you can see in the regression statistics, adjusted R-square slightly increased from 0.28 to 0.29. Meanwhile, the standard error decreases from 58.49 to 58.07. In the second table, the F value significantly increased from 9.39 to 16.44. And looking at the coefficients, the new equations for sales is now minus 284.73 plus 37.53 engine size minus 0.68 horsepower plus 4.71 wheelbase minus 46.45 curb weight. Taking the same example, horsepower, I can see the distance between predicted values and observations decreases from $240 to $160 here. And last but not least, this is actually the most important, that p-value of each variable significantly decreases to lower than 0.001. What does it mean? It means that this model is better than the previous one. So that is how to run linear regression in Microsoft Excel and interpret the output. If you have any questions, please feel free to leave a comment. For more insights into data, including data collection, data entry, data transformation, and data analysis, either in SPSS or in Microsoft Excel, please subscribe, listen, and watch our content that is available in text, audio, and video format. Thank you for being with me today. I'll see you next time in the other videos. Cheers.